October 23rd, 1942, 9:30 in the evening, Western Desert, near the Egyptian town of El Alamein. The first guns of the British Eighth Army opened fire along a front that stretched nearly 40 miles across the desert. More than 800 field guns fired at once. Shells from 25-pounder artillery pieces streaked toward German and Italian defensive belts. Behind them, columns of tanks from the 10th Armored Division and the 1st Armored Division began to move forward through carefully cleared lanes in the minefields. This was the opening of the Second Battle of El Alamein. But the real battle had begun weeks earlier, far from the front line, inside dusty planning tents and improvised engineering depots. Because the Allied problem in North Africa was not only defeating the German Afrika Korps under Field Marshal Erwin Rommel, the real problem was fuel. Mechanized war runs on fuel. Tanks, trucks, armored cars, artillery tractors, aircraft generators. Every mile forward requires a continuous flow of gasoline and diesel, and the desert was a nightmare for logistics. The supply system of the British Eighth Army stretched all the way back to the port of Alexandria, more than 200 miles from the fighting front. Fuel arrived in steel drums loaded on cargo ships, then moved by rail or truck across Egypt. Each drum held 44 gallons of fuel. Each British Sherman tank burned roughly 1 gallon per mile under desert conditions. A single armored division required thousands of gallons every day simply to stay operational. If the supply trucks stopped moving, the tanks stopped fighting. General Bernard Montgomery understood this immediately when he took command of the British Eighth Army in August 1942. Montgomery refused to launch a major offensive until his supply system could guarantee continuous fuel delivery. His quartermasters calculated that the Eighth Army would require more than 1 million gallons of fuel during the opening weeks of the offensive. Transporting that amount by truck alone was dangerously inefficient. A typical 3-ton transport truck consumed nearly 1 gallon of fuel every 6 miles while hauling cargo across desert tracks. Many trucks were effectively burning the same fuel they were trying to deliver. Even worse, German air reconnaissance regularly targeted the long columns of Allied fuel trucks moving across the desert. One bomb on a convoy could destroy thousands of gallons of fuel in seconds. British engineers began searching for a different solution. Among them was an officer in the Royal Engineers named Arthur Hartley. Hartley had spent years working in civilian petroleum infrastructure before the war. He understood pipelines. In civilian oil fields, pipelines carried fuel across hundreds of miles without the need for trucks or trains. The idea seemed simple: build a fuel pipeline across the desert. But nothing about the western desert was simple. The terrain was hard, packed sand mixed with jagged rock. Daytime temperatures climbed above 100 degrees Fahrenheit. Steel pipes expanded and contracted violently between day and night. Sandstorms buried equipment. Vehicle engines failed constantly. Compass navigation was often unreliable. Still, the engineers began work. Using 6-inch steel pipe sections, Royal Engineer construction companies began laying fuel lines east of El Alamein. Pumping stations were installed every few miles to maintain pressure inside the system. The pipes were partially buried to protect them from aircraft observation and artillery fragments. Teams worked at night whenever possible. By October 1942, a growing web of pipelines began linking coastal fuel depots to forward storage tanks closer to the battlefront. Fuel could now move quietly beneath the sand, while the trucks carried ammunition and food instead. Strategically, this changed everything. The British Eighth Army could now store massive fuel reserves only miles behind the assault formations, preparing to attack Rommel's defensive line. Montgomery knew that if his armored divisions broke through, they would need immediate fuel to pursue the retreating German forces west across Libya. Without fuel, victory at El Alamein would stall within days. With fuel, it could become the beginning of a continental retreat for the Axis army. But there was another realization forming inside Allied headquarters. If pipelines could carry fuel across the desert, could they carry fuel across the ocean? Because planners in London were already thinking about a far larger invasion, one that would require millions of gallons of fuel to reach armies fighting on the European continent. And ships carrying fuel were dangerously vulnerable to German submarines. Somewhere in the British engineering community, a radical question began to form. What if fuel did not need ships at all? What if it could travel unseen beneath the water, directly from Britain to an invasion army in Europe? The idea sounded impossible, yet within 2 years, that impossible pipeline would begin crossing one of the most dangerous stretches of water in the world, the English Channel. But first, the engineers had to prove the concept could survive war, and the desert of North Africa would become the testing ground. Because even as the Eighth Army began advancing after El Alamein, the pipeline experiment faced its first real test. The Allied tanks were moving west, faster than anyone expected. And the question now was simple. Could the pipeline keep up with an advancing army? Or would the entire system collapse under the pressure of modern mechanized war? November 4th, 1942, 6:15 in the morning, west of El Alamein, Egypt. Columns of Sherman and Crusader tanks from the British Eighth Army pushed west along the coastal road toward the Libyan frontier. The German line had broken during the night. Units of the German Africa Corps and Italian armored divisions were withdrawing rapidly toward the west. Field Marshal Erwin Rommel understood that his defensive line could not hold against the growing pressure from the Eighth Army, but retreat in the desert created its own crisis. An army that advances too quickly can outrun its fuel. Montgomery staff officers studied the situation carefully. If the Eighth Army lost its supply of gasoline during the pursuit, the German forces could reorganize and establish a new defensive line farther west in Libya. That could delay the Allied advance by months. Inside the logistics headquarters of the Eighth Army, engineers from the Royal Engineers pipeline companies received urgent orders. The fuel line must move forward. This was not a simple repair job. It required extending hundreds of miles of steel pipe across shifting desert terrain while a mechanized army advanced ahead of it. Each section of pipe measured roughly 20 feet in length and weighed several hundred pounds. Teams of soldiers unloaded the pipe from transport trucks and aligned them across the sand using portable pipe stands. Welding teams worked in rotating shifts, often through the night. Each joint had to be sealed perfectly. A single leak in the line could drain thousands of gallons of gasoline into the desert sand. Behind the construction crews came pumping station units. These stations used heavy mechanical pumps powered by diesel engines to maintain pressure inside the pipeline. Without constant pressure, fuel would not travel across the long distances required by the advancing army. The engineers calculated the required flow rate carefully. A pipeline moving fuel at steady pressure could deliver tens of thousands of gallons every day without a single truck leaving the depot. That meant fewer vehicles on the desert tracks, fewer targets for German aircraft, and more fuel reaching the tanks that needed it. Strategically, this created a quiet but powerful advantage. German forces in North Africa relied heavily on fuel shipments transported across the Mediterranean Sea from Italy. Those shipments were constantly threatened by Allied naval patrols and aircraft based in Malta. Fuel shortages had already crippled several German offensives earlier in the campaign. Now the situation was reversing. While the Axis struggled to deliver gasoline to the front, the Allies were creating a buried fuel network that expanded with every mile of their advance. By December 1942, pipeline construction units had extended the system hundreds of miles westward across Egypt and into eastern Libya. Fuel flowed forward through buried steel arteries. At the same time, planners in Britain were watching the results closely. One of the key figures studying the desert pipeline success was engineer Arthur Hartley. His earlier civilian work with oil infrastructure made him one of the few men who fully understood what pipelines could accomplish under extreme conditions. Hartley began discussing a far more ambitious project with British naval planners. The upcoming invasion of Western Europe would require enormous fuel supplies. Tens of thousands of vehicles would land during the first weeks of the invasion. Tanks such as the American M4 Sherman consumed gasoline rapidly during combat operations. Transport trucks and armored vehicles required even more. Fuel ships could deliver gasoline to captured ports. But there was a dangerous gap in that plan. The Allies could not guarantee that major ports would be captured intact during the early days of the invasion. German forces were expected to destroy harbor facilities during any retreat. Without functioning ports, tankers carrying fuel would have nowhere to unload. That meant the invasion army could stall on the beaches. The solution required a new kind of engineering, a pipeline that could run beneath the English Channel. The project soon received a code name, Pipeline Under the Ocean, or simply PLUTO. The concept required solving problems that had never been attempted in wartime engineering. A pipeline placed on the sea floor had to withstand ocean currents, pressure from hundreds of feet of water, and possible damage from naval activity. It also had to carry large volumes of gasoline without leaking. Engineers developed two experimental designs. One design resembled an armored electrical cable, flexible enough to be rolled onto massive spools. The other used rigid steel pipes welded into long sections and laid across the seafloor by specialized ships. Testing began along the southern coast of England during 1943. Early trials revealed serious difficulties. Some sections ruptured under pressure, others twisted when lowered into the water. Pumping gasoline across long underwater distances required extremely powerful pressure systems. Still, the lessons from North Africa provided confidence. The desert pipelines had already proven that fuel could travel long distances without trucks. Now the engineers had to prove that the same idea could cross an ocean. Because by early 1944, Allied commanders were preparing for the largest amphibious invasion in history, an invasion that would land armies in northern France, an invasion that could not succeed without fuel. And if PLUTO failed, thousands of Allied vehicles could run dry only days after landing on the beaches. For the engineers working along the English coast, the pressure was enormous. They had only months to solve a problem no one had solved before. How to pump gasoline beneath the English Channel while an entire invasion army waited on the other side. And the first full-scale test was about to begin. June 6th, 1944, 6:30 in the morning, the coast of Normandy, France. American, British, and Canadian forces were landing across 5 invasion beaches. Infantry from the United States. First Army moved inland from Omaha and Utah beaches, while British and Canadian divisions advanced from Gold, Juno, and Sword. More than 5,000 ships had crossed the English Channel during the night. But the true test of the invasion would begin after the first landings. Armies move on logistics, and the Allied invasion force required enormous quantities of fuel to continue moving across France. Within the first weeks after the landing, mechanized divisions began arriving in Normandy. American armored units such as the 2nd Armored Division and the 3rd Armored Division brought hundreds of M4 Sherman tanks, tank destroyers, half-tracks, and transport vehicles. Each vehicle burned gasoline rapidly during combat operations. A Sherman tank could consume several hundred gallons of fuel during extended maneuver. Supply trucks moving ammunition and food burned nearly as much. The Allied command understood a simple calculation. If the fuel stopped, the advance across France would stop with it. At first, fuel arrived across temporary artificial harbors known as mulberry harbors. Tankers unloaded gasoline into flexible storage tanks along the coast. From there, fuel moved inland by tanker truck. But the Allied advance soon began moving faster than expected. By July 1944, engineers along the English coast began activating the system that had been planned months earlier, pipeline under the ocean, PLUTO. The first operational line ran from the Isle of Wight across the English Channel to Cherbourg in northern France. This route covered roughly 70 miles of underwater distance. The pipeline itself resembled a massive armored cable. Inside the steel exterior ran a narrow tube designed to carry gasoline under high pressure. Powerful pumping stations on the English coast forced fuel through the pipeline toward France. Each station used heavy industrial pumps originally designed for large oil refineries. Engineers monitored pressure constantly to prevent ruptures. The first successful fuel flow through PLUTO began in August 1944. At first, the volumes were modest, but the system expanded rapidly. Additional pipelines were laid from the southern coast of England toward the French port city of Boulogne after it was captured by Allied forces. These lines used rigid steel pipe sections welded into long lengths and placed along the seafloor by specialized cable-laying ships. By autumn 1944, the pipeline network was delivering hundreds of thousands of gallons of gasoline every day. Strategically, this was a quiet revolution in wartime logistics. Instead of relying only on vulnerable tanker ships, the Allies now possessed a direct fuel connection between Britain and the advancing armies in Europe. Fuel pumped in southern England could reach storage depots in France within hours. From those depots, tanker trucks and rail systems distributed gasoline to American and British armored divisions pushing toward Germany. Commanders such as General Dwight D. Eisenhower understood the importance of the system. By late 1944, the Allied advance had stretched hundreds of miles across France and Belgium. Armored spearheads raced toward the German border. This rapid advance created a new challenge. The famous Red Ball Express truck system carried enormous quantities of fuel across France. Thousands of American transport trucks ran almost continuously between coastal depots and the front lines. But the trucks alone could not sustain the growing demand. The PLUTO pipelines continued feeding gasoline into the supply network behind the advancing armies. Over the course of the war, the PLUTO system delivered more than 170 million gallons of fuel from Britain to the European continent. To the soldiers driving tanks and trucks across France, the pipeline was invisible. They saw the fuel trucks, they saw the supply depots. But far behind them, beneath the cold waters of the English Channel, gasoline moved steadily through steel arteries laid by engineers who rarely appeared in wartime headlines. Strategically, the impact was enormous. Reliable fuel supplies allowed Allied armored divisions to maintain pressure on retreating German forces after the breakout from Normandy. The rapid pursuit across France prevented German commanders from forming stable defensive lines until they reached the borders of Germany itself. Mechanized warfare demanded constant motion, and motion demanded fuel. The desert pipelines of North Africa had proven that buried fuel networks could support advancing armies across harsh terrain. PLUTO expanded that idea across an ocean. It was not a weapon. It did not fire shells or drop bombs. Yet it quietly solved one of the most dangerous logistical problems of the war. Because without fuel, the tanks that liberated Western Europe would never have moved beyond the beaches of Normandy, and the pipeline beneath the channel ensured that they never ran dry.